In the last video, we saw that you can generate an EMF using a little wire and a magnet. And that all you need to do if you want to do this is move the magnet. So if I have some mechanical means of moving a magnet and I have a wire, I can generate electricity. And this is great because it's really, really easy to get mechanical means to move a magnet. For example, you can do that with water. You can do this using nuclear power. You can do this using animals, and you can do this yourself. So once we discover a way to generate electricity with mechanical means, what we have done is pave the way for an industrialization of electricity, for a large-scale deployment of electricity. And it's thanks to this that we now have electricity in our homes. And today we're going to see how this electricity works and the kind of current that we have and the properties that the electricity we have in our homes have. And you'll see that it's very, very different from the one that you learned about in the IGCSE or before, where you just have a battery and a light bulb and so on, because we don't have a battery anymore. What we have is a current caused by a magnet that goes up and down, and when this happens, what we get is a current that keeps fluctuating to the sides. It alternates between going this way, this way, this way, this way, this way, and that's why we call it alternating current. Now, what I'm showing you here is not exactly how alternating current works. It's a very simplified scheme, but the basic idea is the same. So I have two magnets, north and south. So there's a field going from here to here. Now, here I have a coil, and what I do is rotate it around this axis here. And this will create an oscillating flux. Now, let's imagine that I'm rotating this with an angular velocity omega. And when this starts, the flux is parallel to the normal to the surface, so this should go with the cosine, right? So we have that the flux should be equal to n, in this case, well, in this case we just have one wire, so n is 1, but let's just write an n just in case we decide to put more wires later. So n times the magnetic field that goes through, that's always constant, times the area of our wire, and then times cosine of the angle, and the angle is changing all the time according to this angular velocity, so times the cosine of omega t. This is our flux, and once we have our flux, we're done, because we can easily calculate the EMF that this thing here generates. So let's do that. So, well, we know that the EMF, and I'm just going to calculate the absolute value, so I'm not going to worry about negative signs, and so I'm just going to take the absolute value of the derivative of the flux with respect to time, and then I'm going to get n b a omega sine of wt. And this is a typical signal of alternating current in our house. Actually, this is the formula that alternating current in our house follows. The only thing that changes is this, which I think in Europe is around 60 hertz, if I'm not mistaken. Now let's see how this would look in a graph. Well, in a graph, this would look something like this. So here we have the EMF, here we have the time, and this would do something like this. Up, down, and so on. And what's funny is that you can see that the voltage is positive here, but it's negative here, and sometimes it's 0. So it keeps changing all the time. We don't have the same voltage all the time, and we don't have like a positive, then negative, positive, then negative. We just have something that oscillates, really goes from 0 to positive, then to 0, then to negative, and so on. So this has a very, very different characteristics to the usual voltage that you're used to, which is just 10 volts. Done. However, we can still figure out some characteristics from this and use them to calculate the properties that our current is going to have. So the first thing that we can see is that there's a maximum voltage, which is going to be equal to whatever it is that multiplies the sign. So in this case, this NBA omega thing, we can call it V0, and this is going to be the maximum voltage that we have. We can also call it E0 for maximum EMF. It depends on the day you'll see me do it this way or this way. For the moment, we're going to stick with this one. So what we have is that the EMF really is just some E0. We don't care how we got that, but we know that it's actually due to this thing. And times the sine of omega t. Well, that's easy. Now what we should do is figure out how the resistance works. Now, in the case of the resistance, all we need to do is use the formula that we already know. So we've got that, well, we've got that our EMF is E0 sine of omega t, and that you know that the current is just the EMF over the resistance. So it's going to be E0 over R sine of omega t. And of course, we can just call all this thing I0 for the maximum current. So we're going to have exactly the same thing. There's a maximum current that depends on the maximum voltage in the usual way, and then of course times sine of omega t, but because this thing keeps oscillating like this one here. Now, how about the power? Well, power cannot be negative. So if we're doing things properly, power better not be negative or we will be in trouble, right? Now, we know that power can be calculated as the current times the EMF. And we have both, right? So we have the current is E0 over R, and then the EMF, well, sorry, times sine of omega t, and then the EMF is E0 sine of omega t. So of course, this will be equal to E0 squared over R sine squared of omega t. And the good news is that this thing here is a square, so it cannot be negative. So our power, as we thought, will always be positive. And that's very good news. Now we can expand this as a function of what we had before. And remember that E0 could be calculated using the n, the omega, the b, and stuff. So we could do this if we want. And this will be equal to the angular velocity times n times v times a squared over r times sine squared of omega t. Normally we will just use this because we will not know how we're getting this alternate current. We will just know the maximum value of the voltage. However, it may be that in some circumstances you know all of this and then you can just calculate T0. Now we have all these quantities, the EMF, the current, and they all oscillate a lot. And this is not very handy when we're trying to make quick calculations. So what we would like to have is some kind of average of this thing. Unfortunately, the main candidate, which is just taking an average, doesn't work. As you can see, the average of this thing is 0. So we just can't use averages for the EMF and the current, which is just the same thing, but instead of E0, there's I0. So we need some other kind of mathematical object to represent this average. And what we're going to use is something called the root mean square. And the root mean square just means doing this. Well, I take this thing and I square it so that it's always positive. Then I take the average of that, and then I take the square root. And that will be a kind of average of my EMF. So let's do that. Now there's two ways of doing this. One's the quick and dirty way, and the other one is the mathematically sound way. I'm going to do it the mathematically sound way, and then I'm going to show you the quick and dirty way. So in the mathematically sound way, all I do is I take this thing here and I square it. So E squared equals E0 squared sine squared of omega t. And then I need to use a trigonometrical identity to get rid of this square over here. And the identity that I'm going to use is that the sine squared of theta is equal to 1 minus the cosine of 2 theta divided by 2. So all I need to do is then replace it over here, and I get that E squared is E0 squared over 2 times 1 minus cosine of 2 theta, well, of 2 omega t. And then what I realize is that this is an oscillating function that also goes positive, negative several times. And therefore the average of this is 0. So I can just get rid of this. And all I'm left with is this term here. So the average of the EMF squared is just E0 squared over 2. And now all I need to do is to square root this. And then I get that the E root mean squared is the square root of this thing here, which is just E0 over the square root of 2. And I can do the same thing for the current, and I will also get that the current root mean squared is I0 over the square root of 2. Now there's another way of getting this, which is just taking a look at this graph and saying, okay, so what happens if I square this thing here? Well, I'm going to get something that goes further up and never reaches negative. So this will be the lowest point. So we'll go further up, then down. Then this will also be at the same height as this. So we'll go further up, down, like this. So it will be just like a sine, but displaced over here and twice as tall. So let's just draw it. It will be something like this, right? Well, that wasn't the best drawing in the world, but you get the idea. And this thing here is E0 squared, right? So then I ask myself, what's the average of this? Well, there's just as much here as there's here, so the average is exactly this, half of it. So the average of this will be E0 squared over 2, which is what I found with my mathematically sound way. Whatever you prefer to do, you'll get to the same result, and then you get these two things here. Now what I would like to do is to take a look at the average power and see how it compares to the root mean square quantities that we just found. So remember that the power is equal to E times I, which is equal to E0 I0 sine squared of omega t. And in this case we can calculate just the average. This is not the root mean square, this is the average, because this is already positive. And remember that the average of this is just 1/2 of this, because the average of the sine squared is 1/2 as we saw before. So then the average power, remember this means average, is going to be E0 I0 over 2. And I can of course separate these two things and make it as E0 over square root of 2 times I0 over square root of 2. But this is nothing but E root mean squared, and this is nothing but I root mean squared. Which means that the root mean square values of the EMF and the current give us exactly the average power. So they work as we would like them to work. Now that we have a very handy way of generating electricity with a rotating coil, it would be very handy if we could know how to use this to transmit this electricity to an actual circuit. And to do this, we use something called the slip ring commutator. And the idea is that each part of this wire is connected to one of these rings that are connected to a brush. Now this means that these rings are allowed to rotate. So both of them can rotate, and then the electricity gets transmitted to the brush this way. Now as this rotates, these things rotate along their ring. So this is connected to here, rotates with its ring, keeps going like this. This thing is here, rotates with its ring, keeps going like this, which ensures that the potential difference here is transmitted to the potential difference between these two wires, and therefore between here and here. And then here I can just connect whatever circuit I please with light bulbs, capacitors, whatever I want, and it will work fine. So again, the idea is I connect each of these two things to a ring that can rotate freely next to a brush, and then the potential difference between these two places that's generated by the magnet will stay between here and here. Now you may have seen this thing called the transformer in the IGCSE, but now we're in a position to actually calculate things with it and show you why it works. And the idea is that we use the fact that our EMF is oscillating to generate an oscillating magnetic field that will generate again an EMF, because remember that only if the magnetic field and therefore the flux is changing, we can generate an EMF. So we could never do this with direct current, because then we would have a potential difference, would always be the same. It would generate a magnetic field here, but there would be no change. So this would not feel a thing. There would be no generated voltage. However, since this is changing, this generates a changing magnetic flux, which generates a changing EMF in here. So I can transmit EMF from here to here, even though these two things are not touching at all. And the way I transmit all this energy is through the magnetic field in this iron core. Now this is an iron core, and the reason this is an iron core is that it doesn't let the magnetic field lines escape. So this is generating a magnetic field that goes around this, and thanks to the fact that this is an iron core, these magnetic field lines are confined in here and they don't get lost and go around there. Because if they did, we would be losing some energy, and then all our calculations wouldn't work anymore. Now, in here there's a certain current that generates a changing flux. And just like the equation works one way, it also works the other way, which means that whatever voltage is here, V1, will be equal to the number of coils, N1, times the change in flux that it generates. Now, for this thing here, I will have exactly the same thing, it's just that it's the flux that generates the voltage. But again, it's exactly the same thing. So I've got that V2 will be equal to the number of coils that this thing goes through times, again, the change in flux. And now we can easily see that this has to be the same in both, because it's the same flux that's going around this thing. So all we need to do is put these two equations together. Now, if I rearrange the first one, I get that the change in flux will be equal to V1 over N1, and also be equal to V2 over N2. And this tells me then that V1 over V2 has to be equal to N1 over N2. And that's why transformers work. All I need to do is get different number of coils around the iron core, and then I can transform the voltage, make it higher or lower according to whatever I need at that time. Now let's think for a moment about what will happen to the current. Now remember that energy has to be conserved, and this happens always. Whether we're doing electricity, kinematics, whatever we're doing, energy has to be conserved. Therefore, the power that goes in has to be the power that goes out. Now, imagine that I have a certain power in. So the power in, power 1, will be equal to V1 I1, and the power out will be equal to V2 I2, and both have to be equal. So this has to be equal to this. So now all we need to do is put these things together. We have V1 I1 equals V2 I2, which means that V1 over V2 has to equal I2 over I1. Be careful, this is the opposite relationship. And then this means, using this thing over here, that I2 over I1 will be equal to N1 over N2. And this means that while I can make the voltage higher using this, if I do this, then I'm going to make the current smaller. And that's because if I didn't do that, I would actually be increasing the power and energy wouldn't be conserved. And then I would be able to generate energy for free, and then the world would end. So this is a necessary consequence of energy conservation. The last thing we need to talk about, and you've probably done this in the IGCSE, is how we actually transmit power to the world. Yeah, these are power transmission lines, believe it or not. Okay, it's not my thing. Anyway, so imagine that here I have this electricity producing central, and I'm transmitting power over to this wire, and then of course I have kilometers of wire, and these wires have a certain resistance, and you know that the dissipated power is I squared R, which means that the more current, the more power this thing is going to dissipate. So what I want to do is I want to make sure that the current is as small as I can make it. In order to do this, what I need to do is I use a transformer here in between. So I put things in a transformer, and then I transmit things over there so that I make the voltage very, very, very high, and then the intensity the current will be very, very, very low, and therefore the power losses will be minimal. The problem is, of course, once this gets to my house, I can't use that, because if I have a 40,000 volt socket, I will be in very, very big trouble if, I put my toaster in it. So what we need to do is then to change the voltage back to something more reasonable, and then this will increase the current. And to do that, of course, all we need to do is to use another transformer, this time a step down transformer, because it goes from high voltage to low voltage, and this will give us a lower voltage and a higher current. And here we don't mind anymore because our wires are very short and the losses because of resistance are negligible, and sometimes we even want them. Alright, so we come to the end of the lesson, and this is just the objectives that I didn't post at the beginning because I thought it would be pointless. This is what you should be able to do after the lesson is over. So first thing, you should know how the AC generator works, and if possible, use equations to describe it. Then you should know how a transformer works, and again, use equations to deduce how its operation. So N1 over N2 and all that stuff, which is what we just did. Then you should know what the root mean square means, and peak current, the V0 and E0, and peak voltage means. So basically the maximum voltage and current. And finally, you need to know how to calculate the average power. Remember, we did this. You just do this using the root mean square, current, and voltage. And that's all. I think this is our last video. From here on, lessons will not be flipped because there's no point. A lot of it requires a lot of discussion, and a lot of it is just not hard enough. So there's no point in having to practice that much. So anyway, I'll see you next day, and hope you enjoyed this last video. Bye.